Hi everyone. This set of slides is going to go over three topics: stoichiometry, the mole ratio, and mass to mole stoichiometry. So let's get started. Stoichiometry involves basic math, and it's the math that we do in chemistry in order to figure out how much product a certain amount of reactant will make, or how much reactant we need in order to make a certain amount of product. Stoichiometry can be difficult if your math is not the strongest, and when we add in chemistry, it can make it even more confusing. But you probably do this kind of math all the time. So, for example, let's say an experiment calls for 3 beakers and 2 test tubes. If we have 20 students working in the lab and they're working in pairs, how much glassware do we need? So, we have to start with what we know. We have 20 students and they're working in pairs, which means that we have 10 pairs. We know that we need 3 beakers for the experiment, and we have 10 pairs, so we can multiply that together, and we know that we need 30 beakers. We also know that we need 2 test tubes, and we have 10 pairs, so we'll need 20 test tubes. So stoichiometry is pretty basic, but sometimes when we add in the chemistry, it gets confusing. But maybe come back to this idea that it's a lot of just multiplication. Okay, so let's move on. So another example that we can look at, we've got a ham sandwich here. Let's say that this ham sandwich is made out of 2 slices of ham, which we abbreviate as H, 1 slice of cheese, which we abbreviate as C, 1 slice of tomato, which we abbreviate as T, 5 pickles, which we abbreviate as P, and then 2 slices of bread. And then if we wanted to write an equation for the sandwich, we can write it like this. We need 2 slices of ham. It's 2 separate slices of ham. So that's why we have the coefficient of 2. And then we also need 1 slice of cheese, 1 slice of tomato, 5 separate pickles. That's why we have a coefficient of 5. And then 2 separate slices of bread. It's coefficient of 2. And when you add all of these reactants together, you would make one product. So this would be our H2CTP5B2, or our ham sandwich. So this would be like a synthesis reaction. You have all these reactants, and then you end up making one product. And then you should notice that all of the coefficients turn into subscripts because now they're a part of one molecule. So we have one molecule. The coefficient for this molecule is 1. And here's my one molecule. It's going to be my ham sandwich. And it's made out of a bunch of separate, we'll say kind of like atoms. It's made out of a bunch of separate atoms or different elements. Okay, so there's our equation. Let's say that some of your friends are coming over and you need to make 5 ham sandwiches. So that means you need to make 5 of this molecule, H2CTP5B2. That's why we have the coefficient of 5. So how much of each ingredient do you need? So for this, we can use conversion factors. So we have one recipe for the one molecule of ham sandwich. We want to make 5 different ham sandwiches. And so we're going to use these conversion factors, which you guys have used before, but you might not know that they were called conversion factors. So we're going to start with what we know. We know we need to make 5 of these ham sandwiches. And then here are my conversion factors. This one is my conversion factor for ham. I know I need 2 slices of ham for each sandwich. So 2 H's for every 1 H2CTP5B2. And then to do the math, you would multiply across your numerators and then divide across your denominators. So 5 times 2 is 10. 10 divided by 1 is 10. So we need 10 slices of ham. The other thing we should notice is we should be able to cross out our units. So here's my H2CTP5B2. And then down here, also my H2CTP5B2. So that just leaves behind my other unit, which is ham. And then here's another example of our conversion factor. We have 5 H2CTP5B2. And then we know that we need 1 slice of cheese for each sandwich. And so that's my other conversion factor. So then 5 times 1 is going to be 5. Then we divide by 1, and that gives me 5 slices of cheese. We could also do conversion factors for the tomato and the pickle and the bread. And if you want to do that, you can go ahead and write those out. But we're going to move on. So let's look at more of a stoichiometry-like problem. Let's say Opie has 8 slices of ham, which is a limited resource. That's all we have. If he wants to use up all of the ham, how many pickles does he need? Let's assume that is not a limited resource, that we have lots and lots of pickles, and then we're not going to run out of them. That's going to be important for later. Okay, so there are 3 steps to all these problems. Step 1, you write out what you know, and you also write out what you're trying to figure out. So we call that the known and the unknown. Step 2, you solve. And then step 3, you check if your answer makes mathematical sense to you. So what do we know? We know that we have 8 slices of ham, H. We also know that for every 2 slices of ham, we need 5 pickles. This is our conversion factor. The thing that we're trying to figure out is how many pickles are going to be needed. So we start with what we know. We have 8 slices of ham. Then we multiply by our conversion factor, which is for every 2 slices of ham, we need 5 pickles. Or for every 5 pickles, we need 2 slices of ham. When you set up your conversion factor, you have to figure out what goes in the numerator and what goes in the denominator of your fraction. And remember, we want to set up our equation so we end up crossing out the units. So if our ham is up top, and then our ham has to be at the bottom. So then they'll cross out and that'll just leave behind the pickles. So then 8 times 5 is 40. 40 divided by 2 is 20, so we will need 20 total pickles. Does that make sense to us? Well, we know that for every 2 slices of ham, we need 5 pickles. So we need more pickles than we do need ham. We know that we have 8 slices of ham, and so we're going to need a lot more than 8 pieces of pickle. And 20 is about twice as many as 8, just like 5 is about twice as many as 2, so that answer should make sense to us. And if it doesn't, go ahead and pause this video and maybe re-watch this. Okay, let's move on. So here are some example problems to do to check to make sure that you understand what's going on. Number 1, a smoothie contains 1 banana, B, 4 strawberries, ST, 1 container of yogurt, Y, and 3 ice cubes, IC. Write a balance equation to represent the recipe. 2, write a conversion factor to show the relationship between the number of strawberries and the number of smoothies produced. 3, how many strawberries would you need in order to make 12 smoothies? Go ahead and pause the video and try to do these questions, and then I'm going to go over the answers. Okay, so if a smoothie contains 1 banana, 4 strawberries, 1 container of yogurt, and 3 ice cubes, this is my set of reactants. Remember, you don't need to write the ones for the coefficients if it's only 1. And then we write our product where we stick everything together, and then we're going to convert our coefficients to being subscripts. Now this is all one big molecule, which is our smoothie. And then for our conversion factor, we want to know the relationship between the number of strawberries and the number of smoothies produced. And we already have that in our equation. We need 4 strawberries for 1 smoothie. So you can write it out like this, 4ST for 1 smoothie, or you can say 4ST for every 1 BST4, Y, IC3. And remember, this is our molecule for 1 smoothie. Okay, so how many strawberries would you need in order to make 12 smoothies? Well, we start with what we know. We want to make 12 smoothies, and then we use our conversion factor to figure that out. So I want to make 12 smoothies. Here's my 12 BST4 Y IC3, also known as a smoothie. And I know that I need 4 strawberries for each smoothie. So 12 times 4 gives me 48. And then 48 divided by 1 is still 48. We cross out my smoothie unit, and I'm just left with my strawberry unit, so I need 48 strawberries. All right. So let's go back to chemistry and less about food. Remember that stoichiometry is the math that we do to figure out how much of a product that we can make if we have a certain amount of reactant. Also, how much reactant we need if we want to make a certain amount of product. So we'll be given some information, sometimes in moles, and then we want to use this thing called a mole ratio, and that can help us figure out the amount of the unknown substance also in moles. But first, let's review chemical equations. So there's my skeleton equation. It says N2 gas plus H2 gas is going to yield NH3 gas. How else could we read this? We would say nitrogen gas plus or added to hydrogen gas is going to yield, this is ammonia gas. This is a polyatomic, so we should know that one. Okay, and then we want to balance the equation. So to balance the equation, we count our atoms on the left and right side of the equation. So we have 2 nitrogens here, and then we have, well, let me go to the other side. We have 2 nitrogens here, we only have 1 nitrogen here. We have 2 hydrogens here and 3 hydrogens here. So this equation is not balanced. So if we want to balance our nitrogens, we can multiply this nitrogen attached to my ammonia by 2. And then we'll have 2 nitrogens and 2 nitrogens. That checks out. If I have a 2 in front of my ammonia, that 2 applies to the nitrogen, but that 2 also applies to the hydrogen. So 2 times the subscript of 3 gives me 6 hydrogens. If I want to have 6 hydrogens, then I have to multiply my reactant hydrogens by 3, because then 3 multiplied by 2 gives me 6. So then we check that out. On this side, I have 2 nitrogens. On this side, I have 2 nitrogens. On this side, my reactant side, I have 6 hydrogens. And on my product side, I have 6 hydrogens. This is my balance equation. So how do we read this balance equation? We would say 1 molecule or 1 mole of nitrogen gas added together with 3 molecules or 3 moles of hydrogen gas is going to yield 2 molecules or 2 moles of ammonia gas. Okay. So remember that the coefficients represent the number of molecules or moles in a reaction, and the subscripts are going to tell us how many atoms are in that 1 molecule. Okay, so this is how we would visualize this equation. Here's my 1 molecule or 1 mole of nitrogen gas. Remember, it's a diatomic. Then we have my 3 molecules or 3 moles of hydrogen gas, also diatomic. And then those will combine together to produce my 2 molecules or 2 moles of ammonia gas. And there's my nitrogen in the middle, and then my 3 hydrogens on the outside, and I have 2 of them, so that's why we have 2 molecules. So the other thing we can also see is that we can calculate our molar masses at the bottom. Remember, the molar masses are the weight of the atoms or the moles or the molecules, and we figure that out by looking at the periodic table and adding together the masses that we see on the periodic table. So for example, if we want to figure out how heavy nitrogen gas is, 1 molecule of nitrogen gas is going to be 28.02 AMUs. And then 1 mole of nitrogen gas is going to be 28.02 grams. And remember, if we look at the periodic table, each nitrogen atom weighs 14.01. And so we multiply that by 2 because this is a diatomic element. So 14.01 times 2 gives us 28.02. And then we can do the same thing with our hydrogens, and we can do the same thing with our ammonia gas. So just make sure that you are familiar and understanding where this math comes from at the bottom. If you need to pause the video, you can go ahead and do that. Okay, so the other thing we should remember, a long time ago, we talked about the law of conservation of mass. And so what we're looking at down here is if we add together how much nitrogen we have, along with how much hydrogen we have, that should equal how much ammonia we end up producing. You cannot just invent new mass when you put 2 reactants together, and you also cannot lose mass when you put 2 reactants together. So 28.02 plus 6.06 is going to produce 34.08 grams. So we have conservation of atoms. So we have 1, 2 atoms of nitrogen, 1, 2 atoms of nitrogen on our product side. And then our reactant side, we have 6 atoms of hydrogen in 3 molecules. And then we have 1, 2, 3, 4, 5, 6 atoms of hydrogen on our product side as well. So we are going to conserve the atoms. What goes in also comes out. And we also conserve the mass. What goes in also comes out. Okay, so we were looking at this kind of figure before. If we are given a certain amount of substance that we have in moles, we can use a mole ratio to figure out the amount of unknown substance, also in moles. But what is a mole ratio? A mole ratio is a conversion factor that relates the amount of moles of any two substances inside of a chemical reaction. What does that mean? Um, we'll talk about that in just a second. The numbers in your conversion factor are going to come from the coefficients of your balanced chemical equation. So you need a balanced chemical equation in order to have a mole ratio. So here's my example equation. We have our nitrogen gas added together with our hydrogen gas, and that's going to yield ammonia gas. And there are a couple of different, 6 different mole ratios that you can write for this one balanced reaction. So we can compare nitrogen and hydrogen. And if we do that, we know that we need 1 mole of nitrogen for every 3 moles of hydrogen. So 1 mole of nitrogen for every 3 moles of hydrogen. You can also flip that and say you need 3 moles of hydrogen for every 1 mole of nitrogen. So basically, these are the same mole ratio, but one is nitrogens to hydrogens, and the other one is hydrogens to nitrogens. We can also compare our nitrogens to our ammonias. So we need 1 nitrogen molecule, 1 mole of nitrogen gas for every 2 molecules or 2 moles of ammonia gas. So that mole ratio would be 1 mole of nitrogen to 2 moles of ammonia, or you can flip that 2 moles of ammonia for 1 mole of nitrogen. And then our last mole ratio that we can do is comparing our hydrogens to our ammonias. So then we have 3 moles of hydrogen gas to 2 moles of ammonia gas, which is our mole ratio right here. Or we can flip that and it can be 2 moles of ammonia gas to 3 moles of hydrogen gas. Those are our 6 possible mole ratios. And then we can use that to calculate information that we want from this equation. So for example, there's our equation, nice and balanced. Question says, how many moles of ammonia are produced if 4.20 moles of hydrogen, which is a limited resource, this is all we have, are reacted with an excess of nitrogen? An excess means we have a lot. This is kind of like we were talking about the ham and the pickles before. We have tons of pickles, we're not worried about that, but we only had 8 slices of ham. So in this case, we only have 4.2 moles of hydrogen and we have a ton of nitrogen, so we don't really care about how much we have. But we do want to know how much ammonia can I make if this is all the hydrogen I have. So same steps as before. You write out what you know and what you're trying to figure out, your known and your unknown. You solve using your mole ratio or your conversion factors, and then you check to make sure that your answer makes sense. If you want to try to do this problem before I do, you can pause the video. Otherwise, I'm going to go ahead. Okay, so we know that we have hydrogen gas. We have 4.2 moles of it, and we're trying to figure out how many moles of ammonia gas we can make. So here are my different mole ratios. So I have to figure out which mole ratio is appropriate to use in this case. So in this case, I know I have hydrogens. I'm trying to relate it over to our ammonia gas. So then we have to use a mole ratio that has hydrogens and ammonias in them. So that's going to be this bottom one here. And then I have to figure out, do I put my hydrogens on top or do I put my hydrogens on the bottom? Well, this is what I'm starting with, so I want to get rid of it too. So hydrogens will be on top here, which means in my conversion factor, hydrogens need to be on the bottom. So I'm starting with 4.2 moles of hydrogen gas. And then my conversion factor, I know I need 2 moles of ammonia gas for every 3 moles of hydrogen gas. And I'm going to put the hydrogen on the bottom. So then these end up crossing out. And I'm just left with the moles of the ammonia gas. So 4.2 times 2 is going to give me 8.4. And then 8.4 divided by 3 is going to give me 2.80 moles of ammonia gas. If you need to go over that again, go ahead and pause and rewind. Okay, so let's check to make sure you know what you're doing. Here's another equation. It says 2H2 gas plus O2 gas yields 2H2O liquid. How else would we read that? We could say 2 moles or 2 molecules of hydrogen gas reacts with 1 mole or 1 molecule of oxygen gas to produce 2 moles or 2 molecules of liquid water. Okay, so how many moles of water are produced if 2.4 moles of oxygen, which is a limited resource, are reacted with an excess of hydrogen? Remember, you write out what you know and what you're trying to figure out. You solve, and then you figure out if your answer makes sense. Okay, so we know that we have 2.4 moles of oxygen. We don't know how many moles of water we can make with the 2.4 moles of oxygen. We have to figure out what our mole ratios are. So how much hydrogen do we have for oxygen? How much hydrogen we have for water? How much oxygen we have for our water? And these are the 6 possible mole ratios. Okay, so we're trying to compare oxygen with water. So then we need to use a mole ratio that has oxygen and water, which are these guys down here. We set up our problem. Here is my oxygen on top at the beginning, so it has to be on the bottom of the conversion factor so we can cross these out. And then we'll be left behind with just the moles of water, which is what I'm trying to figure out. So 2.4 moles of oxygen multiplied by 2 moles of water is going to give me 4.8 moles divided by 1, which is still 4.8 moles. So if I have 2.4 moles of oxygen and a lot of extra hydrogen, I should be able to make 4.8 moles of water. Does my answer make sense? Well, I know, looking at my conversion factor, for every 1 mole of oxygen, you end up making twice as much of the water, and 4.8 is twice that of 2.4. So your answer makes sense. Okay, let's move on. Our last topic, mass to mole stoichiometry. So moles are important. Oh, that should say moles. Let me go back and I'll change it later. But moles are important, but in a lab, we will usually measure substances out by mass. So we need to be able to convert between mass and mole, and also mole and mass. So here's our little map of how we get from point A to point B. You start out with the mass of your given, and then you go to your moles of your given, and you're also going to need the molar mass of what's given, and then you can be able to get to the moles of the unknown. So what does that mean? Let's take a look. Let's do an example problem. Here's my equation. This says tin plus 2 moles of hydrofluoric acid is going to produce tin fluoride and hydrogen gas, solid tin fluoride and hydrogen gas. Okay, so how many moles of hydrogen fluoride, also hydrofluoric acid, are required to react completely with 75 grams of tin? And tin is our SN. So there's my equation. There's my question. We start off with what we know, and then we try to solve and then make sure our answer makes sense. What do we know? We know we have 75 grams of tin. We know that the molar mass of tin is about 118.71 grams. Remember, molar mass is in grams because it's the mass of 1 mole, which is 6.02 times 10 to the 23rd atoms or molecules. And then we also should know that for every 1 mole of tin, we are going to also need 2 moles of hydrogen fluoride or hydrofluoric acid. And how do we know that? We look at my balance equation. Here's my 1 mole of tin, and then my 2 moles of hydrofluoric acid. And that's my mole ratio. And what we're trying to figure out is how many moles of hydrofluoric acid do I need to react with the tin? Okay, so we set up my problem. Here is what we start with, 75 grams of tin. And we know that we want to go from grams to moles. So we're starting with grams. We have to get rid of grams. We're going over to moles. And so we start with 75 grams of tin. And we know that for every 1 mole of tin, 1 mole is going to weigh 118.69 grams. This is my molar mass. And then we also know that for every 1 mole of tin, I'm going to need 2 moles of hydrofluoric acid or hydrogen fluoride. And so that's my setup. And check to make sure that your units cross out. So here's grams of tin in the numerator. Here's grams of tin in the denominator. Here's moles of tin in the numerator. Here's moles of tin in the denominator. So that leaves behind the moles of hydrofluoric acid, which is what we're trying to figure out. Okay, so then 75 times 1 is 75. And then 75 times 2 is 150. And then 150 divided by 118.69 times 1, which is 118.69, gives us 1.26 moles of hydrofluoric acid or hydrogen fluoride. Check if your answer makes sense. So we know that the conversion factor is for about every 1 mole of tin, we need twice as much hydrofluoric acid. And so if I'm starting with 75 grams of tin, 75 grams of tin is not quite 1 mole of tin. 1 mole of tin is about 120 grams. So this number is smaller, so we have less than 1 mole than we're starting with. And so if we try to double it, it's not going to quite be 2 hydrofluoric acids. It's going to be smaller than that, but bigger than 1, and it ends up being 1.26 moles of hydrofluoric acid. So that answer makes sense to me. Okay. And we can also go backwards. If we're starting with the moles, we can figure out the mass. So here is another balance equation. This one says 2 moles of hydrogen sulfide added together with 3 moles of oxygen is going to yield 2 moles of sulfur dioxide and 2 moles of water. So the question is, what mass of oxygen gas is consumed in a reaction that produces 4.60 moles of sulfur dioxide? So again, we start with what we know and what we don't know. We try to solve, and then we check if our answer makes sense. So what we know is we have 4.6 moles of sulfur dioxide. We have to figure out our mole ratio. And so our mole ratio is going to be between our sulfur dioxide and our oxygen gas. So we know that we need 2 moles of sulfur dioxide, or we produce 2 moles of sulfur dioxide for every 3 moles of oxygen gas. So here's my mole ratio. And then we also need to figure out molar mass. So the molar mass of oxygen is 32 grams, because if you look at the periodic table, the atomic mass of oxygen is about 16, but oxygen is diatomic. So 16 times 2 gives us 32 grams. You could also write out the molar mass of sulfur dioxide. You don't need it, but you do know it. So if you wanted to, let me try to write this. You could also write the molar mass of sulfur dioxide. Get my A in there because it's still something that you know. Sulfur dioxide. Okay. And what we don't know is we don't know the mass of oxygen that we need. We know the molar mass of oxygen, but we don't know the mass of oxygen that we need in order to make the 4.6 moles of sulfur dioxide. So then we can set up our equation. And we know that we have 4.6, or we want 4.6 moles of sulfur dioxide. We know that for every 3 moles of oxygen, we end up producing 2 moles of sulfur dioxide. And again, we have to put the sulfur dioxide in the denominator of our conversion factor because it's in the numerator to start with. And then those guys will cross out. Then we have our 3 moles of oxygen, and then we have our 1 mole of oxygen is going to be 32 grams. So we're converting from moles to grams, and the moles cross out, and we're left behind with just the grams of oxygen, which is what we were trying to figure out, the mass of oxygen. So then we multiply across the numerator, 4.6 times 3 times 32, and then divide that by 2, and that'll give us 221 grams of oxygen. So what this is saying is that we need to put together 221 grams of oxygen with a bunch of hydrogen sulfide, and that will end up being able to produce 4.6 moles of sulfur dioxide. Does my answer make sense? Well, I guess to kind of figure that out, what you would want to do is figure out the mass of the sulfur dioxide that you're making or you're trying to make. So in that case, something that you can do is we are trying to make 4.6 moles of sulfur dioxide. And you might want to figure out for every mole of sulfur dioxide, how heavy is it in grams? And then you would be able to kind of compare grams to grams of sulfur dioxide and oxygen. Because in our ratio, what we know in our ratio is that you end up having about 1.5 times as much oxygen as you do sulfur dioxide. And so we can figure out the ratio in grams. So the molar mass of sulfur dioxide is about 64.07. And how do you figure that out? You look at the periodic table, you figure out how heavy sulfur is, and then you also figure out how heavy oxygen is. And there's 2 of them, so you'll need 2 oxygens, and then that's how you get 64.07. Okay, so then if I multiply that through, I'm going to pull up my calculator really quick. 4.6 times 64.07 is going to be about 294.72. So let me write that out. Equals 294.72. So basically what this is saying is that I want to make 294.72 grams of sulfur dioxide. How much oxygen will I need? I'll need 221 grams of oxygen. Now that I think about it, this doesn't actually make sense because it's not going to be the same ratio. It's not going to be a 3-to-1 ratio, which is something that we actually talked about in class last week on your guys' pole goal. This is not a 3-to-1 ratio. The mole ratio is for moles. The mole ratio is not for masses like grams. So it doesn't actually work. Just ask yourself if this makes sense, because it won't. But what you should ask yourself is whether or not your setup made sense. And your setup will make sense if you're able to cross out your units: moles of sulfur dioxide, moles of sulfur dioxide, moles of oxygen, leaves behind my grams of oxygen, which is the thing that I want in the end. Okay, so don't do what I did. You can't use a mole ratio when you're looking at grams. All right, so that is it for 12.1, 12.2, and 12.3. What to do next? Check your notes to make sure that you filled in everything you need to fill in. Check yourself. Think about whether or not you feel like you understood the information that we went over. And then you can check your skills by going to Canvas and going to quizzes. There are 3 skills checks. So take the skills checks. And if you score less than 75% on any of those skills checks, you should watch this video again, either parts of it or the whole thing. You can ask for help from a friend or from me, your teacher. And then you could also YouTube another video about stoichiometry, about mole ratios, or about mass to mole stoichiometry, if that would be helpful. The skills checks are 4 questions, so you need to get at least 3 out of the 4 right in order to get over a 75%. All right, good luck, and thanks for watching.